We'll now begin section 8.5, where we'll talk about vectors in the Cartesian plane. Let's begin with a definition for a vector. A vector is a directed line segment. A vector has a starting point and an ending point. The magnitude of a vector describes the distance from the starting point to the ending point. The vector also has direction, denoted by the arrow. We can show a vector in several forms. We can show a vector as a graph, as you see in the pictures, and we can also describe a vector in what we call component form. Component form is a measure of the distance of the vector using a vertical component and a horizontal component. For our vector g, shown in the picture, if our starting point is here, our horizontal component is a positive 4. 1, 2, 3, 4. Our vertical component is a negative 3. 1, 2, 3. If we wanted to write this vector in component form, we would write the vector 4, negative 3 inside these brackets. In looking at our second vector, again, starting at the starting point, which is here, our horizontal component, we would need to go over 1, 2, 3, 4 in a positive direction. And our vertical component, we would need to go up 1, 2, 3 to get to the end of the vector. And so our vertical component would be a positive 3. In component form, we would describe the vector as 4, 3. So again, you want to keep in mind that your horizontal component needs to come first in the vector representation. We are also asked to find the magnitude of the vector. Remember, the magnitude of the vector is simply a measure of the length from the starting point to the ending point. The magnitude of the vector is denoted using a double set of absolute values. That's our symbol for magnitude. And it's found by taking the square root of a squared plus b squared, where a is your horizontal displacement and b is your vertical displacement. Okay, so let's look at an example. Example 1 says that we are given two vectors, u and v, shown in the picture, and we want to construct a graphical representation of u plus v. So to begin, we're going to write each of the two vectors in component form. Now, you want to be careful about the scale on this graph because it's a bit misleading. Note that if we start here and we go over to here, we have actually gone a distance of 1. You see that this is at negative 1, and one jump over is going to take me to 0, and that takes me at a distance of 1. Right? So I'm going to go one more jump. That'll be a distance of 2. Okay, so you want to be sure you're clear there that my horizontal distance is 2. We're going from negative 1 to positive 1. So my horizontal distance moving in a positive direction is 2. My vertical distance is going to work the same way. I'm going to come up 1 unit, 2 units. So I'm going from a negative 2 down here to a 0 up here. And so we're going up, and so we'll use as our component form for u, 2, 2. For vector v, we're going to start at our initial point, which is at negative 1. We're going to go over 1 unit, which will put me underneath the terminal point on the vector, and it'll put me at negative 2. So I've gone to the left 1, so I'm going to say negative 1. And then I need to go up a unit as well. So going from 0 to 1 is a positive 1. So our vector, component vector representation for V is negative 1, 1. Okay, so now that we have that done, we are going to add our two vectors together. Now, when we add the vectors together, we're essentially adding like components. So we're going to add the two horizontal components together, the 2 and the negative 1. Adding that together gives me 1. And add the two vertical components together. 2 plus 1 makes 3. And so this is the component representation of our answer. And now we simply need to draw that answer. So I'm going to pick a place on my graph. It doesn't really matter where I start. And I am going to go to the right one. So remember that that is jumping 2 of these squared off values. So that's 1 unit to the right. And I'm going to go up 3. And I tell you what, let me move this point down just a little bit so that we have a little bit more room. All right, so let's put our initial point here. So we're going to go over to the right one. That would put me there. And then we're going to go up 3. Remember, each jump up is 2 of these squares. So that's 1, that's 2, that's 3. And so our ending point will be here. We're going from the initial to the ending, and we're going to place our arrow on the end. And so this will be our vector u plus v. Okay, let's try another example. Example 2 says, given two vectors u and v depicted in the graph, construct graphical representations for negative 2u, 3u plus v, and u minus v. So again, let's do our component forms for our vectors first. So vector v, going from our initial to our terminal, we need to go to the left 1. So that's going to be a negative 1. And we need to go down 1, 2. So that's going to be a negative 2. Our vector u, our horizontal component is to move over 1 unit on this graph, 1 to the right. And we have 0 for our vertical displacement. We do not need to go up or down any to complete that vector. Okay, so first we want to find negative 2 times u. So essentially what we're going to do is we're going to take negative 2 and we're going to multiply it by our component representation for u. And we'll basically just distribute that negative 2 through that bracket. So negative 2 times 1 is negative 2. Negative 2 times 0 is 0. And now I can come in and actually draw that negative 2u vector. So I'm going to start it maybe here. Again, it doesn't really matter where you start it. Our horizontal displacement is negative 2, so that's going to go negative 2 units to the left. So that's going to be 1, that's going to be 2. And we don't have any vertical displacement, so we'll just leave it right here. We'll connect and put our arrow. So this is going to be negative 2u. All right, let's go ahead with 3u plus v. So again, 3u plus v, we're going to do 3 times the component representation for u plus the component representation for v. Let's do our multiplication first. So 3 times 1 is 3. 3 times 0 is 0. And then remember, you're going to add the two verticals and the two horizontals. So we're going to add the first two components together, the 3 and the negative 1. That's going to make 2. We're going to add the 0 and the negative 2, and that's going to make negative 2. All right, so there is our component form for our answer. All right, let's go ahead and draw it. And so I'm going to put that one up here, I think. I'm going to go right here as a starting point. Let's see, let me give myself a little bit more room because I'm going to need to go to the right. So let's do right here. All right, so we're going to start with a horizontal displacement of 2. So that's 1, that's 2. And then we're going to do a vertical displacement of negative 2. So we're coming down 2. So 1, 2. And we're going to connect those. And this will be 3u plus v. All right, and our last one is going to be u minus v. So we have the u, which is 1, 0, minus the v, which is negative 1, negative 2. And again, we're going to combine like components. So we'll deal with the first two first. So I have the 1 minus the negative 1. That's going to give me 2. And then I have 0 minus a negative 2, which is also going to give me a positive 2. Okay, so here is u minus v, and we just need to draw it. So we are going to go, let's see where we can put it. Let's put it right here. All right, so I'm going to go over 2 to the right, 1, 2, and up 2. And so this will be u minus v. Okay, and one other thing that I want to show you here before we end this presentation is an example of finding the magnitude. Even though they didn't actually ask us to do it on this one, I'm going to go ahead and show you how to. So let's say that we were asked to find the magnitude of v. So remember that it would be written with the double absolute values. All right, we have our component form for v still on the screen. So remember that your formula says that you're going to take your a squared plus your b squared. And so we've worked with this formula before. Our a is going to be our horizontal displacement, so it will be the negative 1. And the b will be the vertical displacement, so it'll be the negative 2. And so really it's just as simple as that. Negative 1 squared is 1, negative 2 squared is 4, and so our magnitude would be the square root of 5. And you can do this calculation for any vector that you have.